Hello everyone. So now that you are all experts in phase lead and phase lag compensators design, we'll see how can we combine both compensators into a single unit to get improvement in both transient as well as steady state performances. Okay? So the resulting compensator is simply referred to as a lead lag compensator. In other words, the objective here is to design a single compensator that would have a transfer function g of c being equal to kc times s plus 1 over t1 over s plus gamma over t1, such that here you have the phase lead part of the entire lead lag compensator, g of c. So this is the lead portion of it, multiplied by the lag portion of the compensator, which would be S plus 1 over T2 over S plus 1 over beta times T2. For this second term here corresponds to the phase lag portion of the lead lag compensator, now combined as a single unit. And there are actually two approaches to design this evolved compensator that combines the lead and the lag compensators as separate units, but combined into a single one here. The first one is simply to say, okay, I'll start off the process by designing a lead compensator to improve the transient performance. And then I'm going to cascade a lag compensator that will be used to improve the steady state performance. Well, the only difference here is that when you will go to the lag compensator, you'll have to consider the lead compensator as part of being inside the open loop transfer function. Whereas previously, when you were designing the lag compensator, when you're looking at the open loop transfer function, there was nothing else. But here, there would already be a lead compensator inside the open loop that you would have to consider, but otherwise, the design remains the same. The second approach is to say, okay, what would happen if I would set my gamma to be exactly equal to beta? And that is interesting because now the entire design is compounded into a single task. Because now it's not about designing a lead totally separately to the lag portion of the lead lag compensator, but now the calculation, say, of Kc, the gain of the lead portion, will be done by using steady state performance criteria typically used to design the lag compensator as a single unit. So to summarize, there are two cases that we'll have a look at. There are two situations. The first one is when gamma is different than beta, situation number one. And situation number two will be whenever gamma is set to be equal to beta. So again, in the first case, this is a traditional design where you first design the lead compensator independently of the lag, and you do so by looking at the transient time domain specifications that this portion is there to meet. And then once this is satisfied, you go about designing the lag portion of the compensator to improve, obviously, the steady state performance, and you just multiply both portions together. This is case number one. Or with case number two, when you go back and you modify this gamma and you set it to be equal to beta, now all of a sudden this becomes interesting because, as I've just mentioned, the calculation of the lead would also depend on the steady state performance. But to begin with, let's have a look at the situation number one, or case number one, where we do things in cascade, or we do the design totally separately in terms of transient specifications and steady state specifications. I'm going to say case one, design, and that is when gamma is set to be different than beta. So what I'm going to do here is simply to summarize or to give you kind of a shopping list of all the design steps that you need to go through to design a phase lead lag compensator whenever gamma is said to be different than beta, without going into the details of said steps, because those steps correspond to what you've learned in the previous lecture where we went deep into the design of phase lead compensator and phase lag compensator as separate units. So the design procedure for this case goes as follows. Procedure. So, step number 1. Given your transient time domain specifications, such as maximum overshoot, settling time, time of the first peak, and things like that, your job here is to calculate the desired dominant pole locations in a complex plane. Complex plane denoted by S star, as usual. So I'm going to say calculate S star based on the time domain transient specifications that you've learned about in previous lectures. And again, those could be such as maximum overshoot, settling time, time of the first peak, rise time, and so on. So that's not too difficult. This is standard procedure whenever you are designing, say, a lead or lag compensator, or in this case, a lead lag compensator as a single unit. That step doesn't change. Now, you shift focus to the phase lead portion of the compensator by solving, or I'm going to say calculating, phi, the missing phase that the lead portion of the lead lag compensator is responsible to contribute to the system overall. And the way that you calculate it, this is again based on the plant transfer function that we've denoted by G of P, like that. Because the plant on its own, without any compensators, would provide some phase or would have a given phase. Now you know that if you want the root locus to go through the desired pole locations that you've calculated in step 1, that means that the phase of the system has to be exactly equal to minus 180 degrees, or minus pi. But the phase of the plant on its own may very well be different than minus pi. And this is where the lead portion of the phase lead lag compensator is coming from. It is to provide the missing phase such that the overall phase of the system, by adding the compensator in the loop, would provide you the minus pi. So calculate phi based on the phase of this transfer function G of P, and so that the phase lead portion of the lead lag compensator contributes that missing phase. Okay, that's easy. Nothing too different in what we've seen when we're designing the phase lead compensator as a standalone unit. Okay, so now in step 3, you're still focusing solely on the phase lead portion of the lead lag compensator. And here the step is to essentially figure out the location of the lead portion, the location of the pole, and 0 of the lead portion of the lead lag compensator. So again, nothing different than the procedure we've seen when we're calculating the lead compensator as a standalone controller. I want to say determine location of pole and 0 of the lead portion of lead lag compensator. And how do we do it again? Well, if you remember the procedure, this is where we use the angle deficiency that the lead has to contribute to make sure that overall we get our minus pi as the phase of the system. So we use that and we actually calculate the phase of our compensator, G, C of S, evaluated at S equal the desired pole location. And we have to make sure that this corresponds exactly to the missing phase, which is phi. Or in other words, we're going to say we want to calculate or look at the phase of only the lead portion again. 1 over T1, all this over S plus gamma over T1, like that, evaluated at S equal S star, and this has to be exactly equal to the missing phase. And the way we do that, again, is by looking at the asymptote technique I've shown you in the previous lecture. So you have the complex plane, real axis, imaginary axis. You have the desired pole locations, S star at some point. So here, the first step was to draw a line parallel to the real axis. Then you drew the line connecting the origin with S star, split that in half, and then that was corresponding to, well, from this half line, you then take the missing phase, phi over 2 on this side, phi over 2 on the other side, like that, and that would give you the position of the pole of the lead compensator, and it's 0 like that. And this is all done through some basic trigonometry, essentially. Fine. So in step 3, that's what I'm referring to when I write that equation here. So we have to ensure that the position of the 0 and the position of the pole of the lead portion only, when you look at the net contribution in terms of phase of that 0 and that pole, you end up exactly at phi. And that was a technique that I've taught you about in the previous lecture. So nothing new, nothing new. And again, it's because we are considering the design as a cascading design, where we first design the lead portion of the phase lead lag compensator, and then we shift focus and we design the lag portion of our new compensator. So that was step 3. Now the only piece missing for the lead portion is to figure out the gain Kc, because again, in our new compensator, there's only one gain, which is denoted by Kc, whereas previously we had a design for a phase lead with its own gain, a phase lag with its own gain as well. But now that we've combined both together, and we more or less assume here that the gain of the lag portion is very close to 1, as discussed previously. So that's why we are omitting or neglecting, if you will, the gain of the lag portion within the lead lag compensator. So again, there's only one gain, and that gain is associated with the lead portion. So we're going to say calculate our gain that we've denoted herein as Kc, like that. And the way we do that is by looking at the magnitude condition. And if you remember, the magnitude condition told us that at the desired pole location, the magnitude has to be equal to 1. But we have to take the open loop transfer function that combines the lead portion, because the lag doesn't yet exist. And even if we would include the lag portion here, because the magnitude or the norm of the lag portion is very close to 1, that's why we can neglect it in this calculation or in step number 4. So we take the lead portion times our plant transfer function that's provided to us, and we calculate the magnitude of those two things connected in series, evaluated at S equal S star, and the whole thing has to be exactly equal to 1. So the plant transfer function, or the system that you are trying to control, is quantified through its transfer function GP that's given to you. The desired pole location was calculated in step 1. So this is a known quantity. You have just figured out this part of the lead compensator by determining the zero location and the pole location of your lead portion of the lead lag compensator, and that was done through the asymptote method by splitting this portion in half and taking, the geometrical / trigonometrical approach that I've taught you about. So that was done in the previous step, so that was step 3. Such that the only unknown that remains here is Kc. So you can solve that. The best way to do it, you could do it directly with this by plugging the desired pole location in terms of complex number in that equation and solving for Kc. That's one approach. Or the other approach is to use what we've used in the past, and that is just a geometrical / trigonometrical, struggling with that word, using trigonometry as an approach, okay? So a graphical way to solve for Kc. So we'd have to figure out the distance between S star and that pole and that zero of the compensator, and between S star and the poles and zeros of your plant transfer function, and solving the whole thing for Kc, essentially, as you've done in the previous design for the phase lag or phase lead standalone compensator. After you've done step 4, you have essentially completed the design of the phase lead portion. Essentially, you have figured out half of the lead lag compensator. Great. That was the hardest part. Because as you know, figuring out a lag compensator in terms of design is very easy. And that begins in step 5. So in step 5, because you are beginning the design of the lag portion of the lead lag compensator, you need to determine what would be the beta factor. Okay? And if you remember beta was determined as function of your KV factor itself, calculated from the steady state tracking error as a specification provided by the customer or the client. So this is given to you, and then you calculate KV, And based on kV that you need and kV that you have with the open loop plant, then you can determine the beta factor, as we've done in the phase lag compensator design in the previous lecture. There's nothing different here. Now, beta corresponds to the relative position of the zero with respect to the pole of the lag compensator. But how do you determine that? Again, just as a refresher, I just told you this is based on kV itself, based on ESS, but to be more explicit, I'm going to give you the equation to do so. So if you remember, kV was determined as being the limit of S towards 0 of S times the open loop transfer function. Now, the only difference now is that because you are designing a phase lead lag compensator in your open loop, you don't only have the lag portion, but there's also the lead portion of it. So you go back and say, okay, limit of S towards 0 of S. What do I have in my open loop? Well, if you remember, what we have now is something like this: reference signal minus the current output of the plant, GP, gives us the error signal. That feeds into our KC S plus 1 over T1 times S plus gamma over T1 times S plus 1 over T2 over S plus 1 over beta T2. Quite messy, but you get the idea. This is our phase lead lag compensator, GFC. That means that our open loop is now this big transfer function related to the phase lead lag compensator multiplied by the plant transfer function denoted by G of P. All right, no big deal. We can just say this is S plus 1 over T1 over S plus 1, or gamma over T1. This is the lead portion, and make sure you don't forget KC in front of it, times the lag portion without a gain that I just discussed with you. So it'll be 1 over T2 over S plus 1 over beta T2, like that. And G of P times the plant transfer function. All this gives you kV. All right. But wait, that can get simplified quite a bit because we're letting S tending towards 0. That's good news, because that simplifies greatly what we have inside our parentheses. Because that would mean that kV, again, limit S towards 0 of S times our big G open loop, which is all of this, will be KC. And all the S terms towards 0 like that. Meaning that we're left with 1 over T1 over gamma over T1, which is 1 over gamma, simply. And here, 1 over T2 over 1 over beta T2 means that we're left with beta simply for this term, and then our plant transfer function that depends on S. Great. It's fantastic, because if you look at what we have now, this is coming from the steady state specification in terms of steady state tracking error that we've denoted ESS like that. Okay, so this is given, essentially is calculated by you. This we know. This is related to the relative position of the pole with respect to the zero of the phase lead portion of the lead lag compensator. So that was determined by you. So that's known. Kc is known as well. That was coming from the lead design portion, similar to the gamma. So both were determined in step 3 and 4 respectively. Step 3 for gamma, step 4 for Kc using the magnitude condition. So this is known. G of P is given to you as the plant transfer function of the system you want to control, such that the only unknown here is beta, which means that you can easily solve that equation for beta. Unknown, or in other words, is what you want to solve for. And so because the only thing now that depends on S is G of P, you could also rewrite the whole thing as simply Kv equal to Kc beta over gamma, and then you evaluate the limit of S towards 0 of the plant transfer function that depends on S, and solve that for beta. Easy peasy, nothing different. All right, step 6, which is the last step of the entire lead lag compensator design whenever beta is different than gamma. Step 6, the last thing is to determine T2 associated with the lag compensator portion of the lead lag design. Because with beta determines the scaling factor that exists between the respective location of the zero and the pole of the phase lag portion of the compensator. But that doesn't tell you where they are exactly in the complex plane. For example, if beta is found to be 10, that could mean that you have, say, a pole at 1 and a 0 at minus 10. This is a beta of 10. That's the scaling factor that exists between those two respective positions. But you could also have the same beta if you would have the pole at, say, minus 30, and then the 0 at minus 300. That would also be a beta of 10. That's the scaling factor that exists between the 0 and the pole of your lag compensator. So both situations give you the same beta factor. So just having beta has a value doesn't indicate where in a complex plane the 0 and the pole of the lag portion of the compensator are. So to determine exactly their position, you need to figure out T2. And as you know, T2 is determined by just a simple rule of thumb. So typically, because we don't want the lag compensator to mess up or to destroy the good design you've come up with thus far in terms of bending the branches of the root locus to make sure that they go through the desired pole location and things like that, and making sure that the poles, the dominant poles, stop exactly at the desired pole locations in the complex plane. that was all handled by the lag, or the lead portion of the lead lag compensator. Now the lag portion is only here to scale the KV factor to ensure that you meet the steady state tracking performance as quantified by ESS, the steady state tracking error. So because you don't want, in other words, you don't want the lag portion to modify the root locus, it means that you don't want them to have an impact. And that translates into having them very close to each other, almost to the point where in the grand scheme of things, they are pretty much irrelevant and they are considered to be on top of each other, thereby canceling their respective effect in terms of the pole and the zero of the lag compensator. So this is why we typically select T2 to be large. And refer to the previous lecture where I talked about the design of phase lag compensator. So you want that factor to be large such that the location of the zero of the lag portion is pretty close to the origin, and such that also the location of the pole is even closer to the origin thanks to the beta factor that exists here on the denominator. Rule of thumb, I often go with T2 equal 10, meaning that this translates into S plus 0.1 and S plus, say, 0.1 divided by beta. Beta could be, say, 10 again, such that you have 0.01. Meaning that you have designed a lag that satisfies the beta requirement in terms of respective position of 0 with respect to the pole, and that would be, say, beta equal to 10 in that case. Yet, they're pretty close to the origin, and you have the 0 here, and the pole even closer to the origin. So when you look at the overall root locus, where you have S star here and things like that, and they move, so like this, I don't know, they do what they have to do. Well, those two things are pretty close to the origin and pretty much on top of each other, won't affect the motion of the poles in the complex plane like that. So you have designed effectively a lag compensator that won't modify the transient response by not affecting the location of the poles in the complex plane, yet would decrease the steady state error by some factor. So once you've designed T2 or selected T2 arbitrarily, you've pretty much completed the entire design of the lead lag compensator as a standalone unit. And if you remember the design procedures for the lead and the lag compensators in the past, you will recognize that here there was nothing new. It was essentially a review of the lead design and of the lag design, just combined together with some minor modifications. Those being that when you go about designing the lag compensator, and if you look at the KV calculation, you need to include the lead portion of it for KV as, the limit of S towards 0 of S times the G open loop, the open loop transfer function of the system, because now not only the plant is in the open loop, but the entire compensator with the lead portion of it is inside the open loop. So that's a slight modification here. And other than that, oh yeah, the only other difference is that you're not calculating a gain in the end for the lag compensator, because you consider that this is pretty much equal to 1. So that is the first situation, or first case, for designing a lead lag compensator, and that was whenever gamma was set to be different than beta. One thing to close up the first case is that make sure that beta times T2, or the position of, that quantifies the position of the pole of the lag portion of the lead lag compensator, is not too large. Because you say, okay, you decided to do the design with T2 equal 10. Well, I'm smarter than that. I'm going to select T2 equal to 1 million, such that they are like essentially at the origin of the complex plane. Well, you have to be careful, because if this quantity, beta times T2, is too large, that would translate in terms of practical applications into a signal, a control signal, because remember always that you have your compensator that calculates U as the control input, and this is fed to the plant or the system that you're controlling. This being too large would translate into a very large and rapidly varying control signal U that might not be physically possible to produce by some actuators that sit right between the software on the computer on board the system and the actual physics. Okay, so here you could have thrusters if you're talking about a spacecraft control system. So U, the output of your compensator, is then being fed to the physical device that is meant to produce the control acceleration and control torques, possibly, to be applied and delivered to the physical system. But those are mechanical devices, so they have a limit as to how much torque or how much thrust they can produce. So if that signal exceeds whatever the actuators are capable of delivering physically, then you're going to run into saturation issues, and that's not good news, because that will throw the entire closed-loop system to behave in a highly nonlinear manner. That means that all the linear approximations that you've based the design on will go to garbage, and then the performance won't be as expected. So just keep that in mind. Don't go too far in terms of pushing T2 to a high value. Typically speaking, between say 10 and 30, 40, maybe 50 would be something acceptable as a range of values, but don't go too crazy on T2, because that would cause some practical problems down the road. Great. So that was easy. Now, let's have a look at something a bit more interesting and different in what we've done so far. That would be case 2. That is whenever we set gamma to be equal to beta. I'll just put it the other way around. So when gamma is set to be equal to beta, such that your compensator, G of C, is now S plus 1 over T1 over 1 plus beta over T1 and Kc, this being the phase lead portion as usual, multiplied by the phase lag, which would be 1 over T2 to quantify the position of the zero of the lag portion, over S plus 1 over beta T2 for the position of the pole of the lag portion. So you see clearly that now this is slightly different, because previously we had gamma here to quantify the position of the pole for the lead portion of the lead lag compensator, whereas now we're using the same scaling factor in both portions of the compensator, that scaling factor being beta. So we'll see how this affects the design methodology. So again, I'm going to go through a step-by-step procedure without spending too much time on the individual step, because they're essentially using the same thought process that we've used so far. So looking at the phase condition, magnitude condition, making sure that the lead portion contributes this amount of phase, and so on and so on. Yet you'll see some nuances compared to the previous designs. So step one. Step one is the same. I want to calculate the desired dominant pole locations based on some transient specifications. So based on maximum overshoot, settling time, time of first peak, rise time, you come up with the desired pole locations in a complex plane, those being denoted as S star as usual. Now in step two, and this is where it's very interesting because now we first start by calculating Kc of the lead portion based on some steady state performance denoted by ESS. How is that even possible? Because before we had to figure out the position of the zero and the pole of our lead compensator, and then we would design its gain, Kc. But now you're telling me that we can jump right away to Kc without even knowing where the pole and the zero of the lead portion exist? Well, yes. Because if you remember, and when I say based on ESS, this implies that this is based on your kV. Because kV is actually the limit of S towards 0 of S times G open loop. Right. What do we have in our open loop? Well, now it's not only a lead or only a lag. Our G open loop is a lead lag compensator. Beta over T1 times Kc times the lag portion, S plus 1 over T2 over S plus 1 over beta T2 times your plant transfer function. Okay. Then what? And this is where the magic happens, truly, because if you go back to kV and you substitute all the S's with zeros, you would be left with a limit of S towards 0 of S times your plant transfer function, which depends on S. This parenthesis would be 1 over T, 1 over beta. Whereas this one would give you beta, right? Because the T2 terms cancel out and you're left with beta. As here the T1 terms cancel out and you're left with 1 over beta. And with Kc, obviously. Don't forget your Kc. Right? That's beautiful because you now have beta over beta. Boom. Canceled. So based on some kV specifications calculated from ESS, all you have to do is to evaluate the limit of S times your plant transfer function, and that is multiplied with Kc, which is the only unknown left in that equation. So in that sense, it is a bit simpler than what we had for the lead lag compensator design using gamma different than beta, because this equation is a little bit more simpler in terms of solving for Kc. Right? This is given in the question, and that was calculated from the specifications and steady state performance. And that's where you really merge the lead with the lag design by designing a portion of your lead compensator based on some transient or some steady state specification, typically only used for the lag portion of the compensator. Nice. In step 3, so that was the end of step 2, figuring out KC. Step 3, you want to calculate the angle deficiency that the lead portion has to contribute. To make sure that you get your minus pi in terms of phase. In other words, to ensure that the root locus would go through the desired pole locations in a complex plane. Or I'm going to say that translates into calculating your phi angle. As done usually. There's nothing different here. All right. And this is where now things are also different. Because if you think about the idea behind the previous design is that we're first calculating the position of the zero and the pole of the lead portion based on the angle deficiency, and then we'll come in and calculate the gain using the magnitude condition to ensure that based on the two locations that we've previously selected that were meeting the phi angle, that would still get a magnitude of 1 overall. But now, because we have already calculated our gain Kc, we cannot use that Kc gain as a way to bring the design together in terms of making sure that the magnitude based on the pole and zero location of the lead comes up to be equal to 1. We don't have that luxury anymore, meaning that now for the location of the pole and the zero of the lead portion, there will be only one solution possible. Whereas previously, there could have been multiple solutions. Right? Because if you remember, real axis, imaginary axis, desired pole locations, we had designed the pole and the zero to make sure that their respective contribution calculated at desired pole location would give us exactly phi. So that would be contribution of the zero minus contribution of the pole equal to phi, or the angle deficiency that the lead has to provide. But there would have been a multiple or a multitude of solutions. You could have placed the pole, the color marker, could have placed a pole here, meaning that the zero would have been here, and yet getting the net contribution to also be equal to phi. Or you could have placed them somewhere else, end up with different pole and zero locations, still ensuring that you get the phi contribution out of the lead compensator. Yes, that's right. I gave you a systematic way to calculate the pole and the zero, tracing that line, connecting that to the origin, splitting in half, and based on that line, half of the missing phase, half of the missing phase, boom, that's your pole, that's your zero. It appeared as if there was only one solution, but in reality, this is just one methodology to easily figure out the pole and zero for the lead compensator, but in practice, there is an infinite number of solutions whenever alpha is or gamma is different than beta. But now, because we cannot use the magnitude condition as a fudging factor to bring the design together in terms of making sure that wherever we're placing the pole and the zero of the lead, their respective distance from S star one over the other with the rest of the open loop transfer functions would be giving 1 in terms of magnitude. The only fudging factor was Kc. In other words, Kc could have been used to accommodate a multitude of positions in the complex plane for the pole and the zero of the lead portion. Hopefully this whole discussion makes sense. I kind of feel like a broken record at that point, but that was the idea. But now that Kc is set in stone, we cannot use that to compensate for the respective distance between S star and the pole and the zero of the compensator to ensure that overall the magnitude remains equal to 1. Well, how does that work? Well, it's going to work similarly. It's just that it won't be a systematic methodology to figure out the location of the pole and the location of the zero for the lead portion. You'd have to work a bit harder because now you have to simultaneously satisfy the phase condition for your lead, evaluated S equal S star. This has to be equal to the phase deficiency calculated in the previous step. But also you have to worry about the norm or the magnitude condition, Kc, of what you have in the open loop, which is the lead lag compensator. Not really, because again here we've always considered that the magnitude of the lag compensator was pretty close to 1. So we kick this out and only include the plant transfer function evaluated at S equal S star. All this has to be equal to 1. Previously, that equation was used to solve for Kc based on the position of the zero on the pole of the lead portion, and that we had selected to make sure that they were satisfying the phase deficiency. But now that this is pre-calculated in step number 2, it means that there's only one solution left that would accommodate both this phase deficiency and this magnitude condition. So I highly recommend that you do that graphically by drawing a complex plane. Real, imaginary. As usual, you have your S star somewhere that you want them to be based on your transient specification. And now you have to ensure that the phase of this minus the phase of that gives you pi, while making sure that overall the distance between S star and the pole of the lead and the distance between S star and the zero of the lead, when substituted back in your magnitude condition, you end up with 1 at the end of the day. Ooh boy, sounds daunting, right? But fear not, I'm going to do a numerical example immediately after this to show you how we can do that. And you'll see that it's not terribly difficult. All right. So we're going to leave this step as it is. Just remember that there's a bit of work involved in step number 4. But that essentially concludes the lead portion of the design, because in step 5, which is the last step, typically this is where you start the lag design by figuring out the beta factor, but here you have already calculated beta in some previous step. I'm going to say given beta, you have to select for yourself T2 to place the pole and 0 of the lag portion of the lead lag compensator inside the root locus. And the only thing to remember is that you want T2 to be positive, obviously, while ensuring that beta times T2 is not too large. I'm going to put too large in quotation marks because it's not quantified in any way, shape, or form. It's just not too large, as we've discussed. Typically, I like to place my pole of my lag at, say, 0.1 kind of thing, or 0.01 for the poles, such that the 0 ends up at 0.1. And overall, in the grand scheme of things, they appear to be on top of each other because desired pole location is way further to the left at minus 2.5 or minus 4, minus 5 kind of thing. So when having things that are almost at the origin on top of each other, you won't affect the root locus anymore. Okay, so that concludes the theoretical discussion on how can we design a lead lag compensator as a single standalone unit instead of designing 2 separate compensators. Although the first methodology we've seen today, whenever gamma was said to be different than beta, is pretty much what I've just described. So you design the lead, and then you go about designing the lag, keeping in mind that you have the lead in your open loop transfer function whenever you use kV equal the limit of S towards 0 of S times G open loop. And also by remembering that you don't have to calculate 2 separate gains for the lead and the lag compensator, or the lead and lag portions, because there's only one gain, being Kc, and this gain we said was associated with the lead portion only. So the lag is only a matter of figuring out the position of the 0 on the pole to ensure that the beta factor calculated previously is satisfied. So that was case number 1. Case number 2, a bit different, yet I think very interesting, because you are mixing steady state performance within the lead design to set the beta factor, because there's no gamma anymore. It's all about beta, and that makes things different and thereby interesting. So to kind of make sure that you are able to wrap your head around the concepts, I'm going to do a quick numerical example for the case number 2 only, because I think case number 1, because we've seen the theory for lead and the theory for lag, the separate units, we did an example for both. You've seen the theory combining them together, so I don't think you need an extra numerical example for case number 1. I think the most interesting example would be for case number 2, when you set gamma equal to beta. So, case 2, gamma equal beta. What does that mean again? It means that your compensator would have the following form, which is Kc times S plus 1 over T1 over S plus beta over T1 times the lag portion, S plus 1 over T2 over S plus beta T2. Nope, 1 over beta T2, sorry. Like that. And this is used to control our plant or to control our system, which is quantified with its own transfer function. That's our good old GFP, plant transfer function. And here we have a transfer function that looks like 4 over S times S plus 0.5. So you have the reference signal. You're going to compare that with the output of your plant, which is Y, plus minus to generate an error signal, which is then multiplied with your controller or compensator transfer function as a single unit. That would generate the control input signal, denoted by U. U feeds the plant transfer function or its dynamics to generate the new output. Compare that again with R, and so on and so on. You close the loop like that. So based on that, we're going to go through the design methodology I've just shown you for case number 2 and see how does that work. Throughout this example, I'm going to take some shortcuts. For example, how to go from specifications to the desired pole location in complex plane. That should be acquired by now. So in step 1, where you have to calculate the desired pole locations in complex plane, the dominant poles, I'm just going to give them to you. In the context of this course, it would either be given to you directly, or you'd have to calculate them based on mapping of the transient specifications, the NP and settling time in terms of omega n and zeta, and based on that calculate the desired pole location, remembering, for example, that the real part is always minus zeta times omega n, things like that, okay? But I'm assuming that you know how to do it on your own. So let's just assume that the desired pole location is minus 2.5 plus minus 4.33 J. That is to meet, I'm going to say some maximum overshoot, settling time, time of first peak, and rise time. All of these being transient time domain specifications. Okay. Then in step 2, what you want to do again is calculate the gain of the phase lead portion of the lead lag compensator, KC. And this is based on some KV value that you want to satisfy some steady state tracking performance provided to you. So let's assume that here, for calculation purposes, we have KV equal to 80, okay? So again, in an exam settling, this quantity could be provided to you directly, or you'd have to do the mapping from steady state tracking performance to KV. But by now you should know how to do it on your own, so I'm not spending time on that. What is interesting here is how to use it to calculate KC. So if you remember, what we had derived previously was that KV was equal to the limit of S towards 0 of S times your plant transfer function times KC only, because the beta factors cancel out. You would have beta over beta. Unlike before, where you have 1 over gamma times beta. But now that beta is equal to gamma, they both cancel out, and you're left with this very simplistic expression that relates KV to KC, which is the static gain of your lag portion of the compensator. Okay, so let's do the work here. I'm going to write down limit of S times our plant transfer function was 4 over S times S plus 0.5 as provided to us times Kc, and limit of s towards 0. Okay, well, we have s here over s, so they both cancel out, such that you're left with Kv equal, you can evaluate the limit of s towards 0 because there's only one s left. That disappears, so that would be 8 times Kc. And because we had Kv given or equal to 80 in this particular example, that means you have 80 equal 8 Kc, and thereby you can finally calculate that Kc is equal to 10. And this is where things get a little bit complicated because, again, Kc cannot be used anymore to compensate for the fact that your pole and your zero of your lead portion of the phase lead lag compensator could be wherever, and use that as a fudging factor in the end to bring the design together to meet the magnitude condition equal to 1. That is now set in stone, meaning that the only location remaining in the complex plane to place the pole and the zero of the lead portion of the compensator is unique. Okay? But before we jump into this, what seems to be a tedious work, in step 4, let's first figure out the phase deficiency that the zero on the pole of the lead portion has to handle. And that is in step 3. Angle efficiency, which is phi. So phi is related to the phase of the plant itself. Because again, the plant has some phase. That phase, most of the time, will be different than minus pi, or minus 180 degrees. In other words, the plant on its own does not generate a root locus that goes through the desired pole location. So you need to bend the branches to make sure that the root locus goes through S star. Okay, so essentially you need to figure out the plant, the phase of the plant on its own, evaluated at S equal S star, and you'll realize that that's not equal to minus 180 degrees. So from this, you would figure out how much phase does the lead lag compensator has to provide to exactly end up at minus 180 degrees, or minus pi. That's your phase condition. So you have this plus contribution of lead lag compensator. I'm going to underline lead because the lag again does not contribute any phase to the system, only the lag portion does. All this has to be equal to minus 180 degrees. That is the phase condition. So again, this is done graphically. So I always like to draw a complex plane like that. This is my way of doing it. You could do it just by plug and play of the complex numbers and this, and figuring out the phase of the numerator divide or minus the phase of the denominator and things like that. I like to do that graphically. So allocate my desired pole location, S star, here. And I go back to my plant transfer function at 4s times s plus 0.5. That was my GP. Like that. So I don't have any zeros, and I have two poles. The first pole is at s equals 0. The second pole is at s equal minus 0.5. One pole, two pole. And I know that my desired pole location, based on my calculation in step 1, was minus 2.5 for the real part, plus 4.33 J for the imaginary part. So to figure out the phase of those two poles evaluated at S star, just draw those lines like this, like that. And I need to calculate those two angles. And because I know this is minus 0.5, this is 0, I know the distance here, or I know the side of this right-handed triangle, all right? That would be 2 in that case. I know its height. I can use some trigonometry to figure out this first angle. And then using another triangle, a larger one, that has a base of minus 2.5, or from the origin all the way to the real part of my desired pole location, same height, 4.33. I can easily use trigonometry to figure out this angle as well. So now I have those two angles, meaning that I know what will be the phase of my plane transfer function, because I know that the phase of this is equivalent of the phase provided by my zeros minus the phase provided by my poles. I don't have any zeros, so that would be 0. And the phase provided by my poles would be this angle plus that angle, but minus. So minus this plus this. Using those numbers, you should end up at 235 degrees. So you have minus 235 degrees of phase provided by the plant evaluated at that particular desired pole location. That tells you that you're not at what you need to ensure that the root locus of just the plant on its own would go through here. And if you were to draw the root locus of these two poles, you would see that they knock somewhere in between. One would fly up, the other one would fly down. So there's no way that you could, by cranking the open loop gain, move those two poles and ensure that it would end up where you want them to be. So to make it happen, you need to introduce additional poles and zeros in the root locus to bend the branches such that they ultimately go through the desired pole location. So bending the branches meaning that you need to add some phase to the system here. So what would be the phase that the lead compensator has to provide? Well, that would be 55 degrees in that case, because you have minus 235 plus phi equal minus 180, right? So this, in terms of number, you figured out that you had minus 235 degrees for this, plus the missing phase, minus 180. That means that phase deficiency is 55 degrees. All right. So I know that this being provided by the lead portion is essentially informing me of the location of the pole and the location of the zero on the complex plane, such that I ultimately get a net phase out of that zero and pole equal to 55 degrees. And that's what we're going to do in step number 4. Where we need to make sure that we simultaneously satisfy the phase and the magnitude condition for the lead portion of the lead lag compensator. Or in other words, in step 4, we need to figure out the position of the zero and the pole of the lead portion. So if you go back to the magnitude condition, that tells you that you take the norm of Kc times s plus 1 over T1 over s plus beta over T1 times the magnitude of the lag, which is 1, so that's not included again, times Gp of s. All this evaluated at s equal s star has to be equal to 1. This I know from step number 2. That was our 10. This I know. This is provided to me. This I don't know. And I don't know this. So in other words, I don't know the position of the 0 and the pole in the complex plane. Interesting. So how will we go about that? I'll show you. So the trick here is to multiply Kc with Gp and to leave this on its own because it cannot be evaluated directly. I'm going to say S plus 1 over T over S plus beta over T1 norm has to be equal to Kc was 10 if I'm not mistaken in our case. Yes. So 10 times G of P. G of P was 4 over S times S plus 0.5. And all of this evaluated at S equal S star, which has to be equal to 1. So let's focus on this only for the moment. All right, I know how to calculate the magnitude of this evaluated at S star, right? Because again, all I have to do is to draw the root, or not the root focus, but a complex plane, locate my two poles of the plant, one at 0, one at minus 0.5, locate my S star, somewhere over here at minus 2.5 and plus 4.33 J. But now we're not talking about phase, but we're talking about magnitude, meaning that we have to use trigonometry to figure out the length of that line connecting S star to this pole at S equal minus 0.5. And again, use trigonometry to calculate the length of this side of this triangle, the big one this time, that connects S star to the pole at the origin. It's only trigonometry because you have everything. You have the size of this base for the small triangle, which would be 2. The size of this base for the big triangle will be 2.5. Yet the height for both triangles would be exactly the same, and in our case would be equal to 4.33. You then have everything you need to calculate those two sides. And if you do things properly, you would end up, let me just rewrite what we have here. For completeness, ten times 4 stays 4, right? Now the norm of the pole at the origin, which is the longest side here, if you do math properly, that should give you 5. That's for the pole at origin. times the length of the side connecting S star to the pole at minus 0.5. That'll be the smallest of the two. And that should give you 4.74. Now this has to be equal to 1. And I would highly encourage you to make sure that you know how to do the trigonometry or the math yourself to calculate the magnitude of those two poles that are part of the plant transfer function with respect to S star, the desired pole location. So in other words, make sure that you get 5 for this side and 4.77 for this other side. All right, so this could be easily evaluated, and that will give you 40 over 5 times this, so 40 over 5, that would be 8. So if you want to leave it as a fraction, and I highly recommend you do, you get 8 over 4.77 like that. That's not that bad, because now, if you look at what you have left, this is set in stone. This is what you need. These are the two variables you can play with. That tells you that the norm of this, evaluated at S equal S star, has to give you the opposite of this fraction. The norm of S plus 1 over T1 over S plus beta over T1 when evaluated S equal S star. This has to give you 4.77 over 8, such that when you evaluate this times 8 over 4.77, you do end up with 1 exactly for the magnitude. Okay. So now, this is where you'll need to work, because so far I would consider this to be work. It's only, elementary trigonometry and triangles, figure things out. So the only step you have left to do within step number 4 is to draw, again, complex plane, real axis, imaginary axis, desired pole location, S star. And now it's up to you to determine the position of the pole of the lead and the zero of the lead, such that this angle minus this angle gives you phi. Okay? While making sure that this side here, which is between S star and the 0, is equal to 4.77. And while ensuring that the distance between S star and this pole, or this, which is on the denominator, has to be equal to 8. So you have two sides, you have an angle difference, and believe me, you have everything you need in terms of trigonometry to figure out the position of the pole and the 0 along this axis. And if you do the trig correctly, you would get the 0 position to be at S equal minus 2.38, and the pole to be located at S equal minus 8.34. Makes sense. The pole is further to the left, the complex plane, compared to the position of the 0. This is the lead portion of the lead lag compensator. And I would highly recommend that you do that as a homework for yourself. Given this length, given that length, given that the angle difference between this and that has to be 5 or 55 degrees, how can you turn those three numbers into a procedure that would allow you to locate the zero and the pole on the real axis? And these are the answers. So do that as a homework for yourself to confirm that you have a procedure in place, that you can take those three numbers and turn that into zero and pole location for the lead portion of your compensator. Because it won't be time to scratch your head during an exam trying to figure this out. Now you have the time to do it ahead of an exam or an assignment. Take time and go back to fundamental trigonometry and triangles and figure a procedure for yourself. Turn those numbers into what you're looking for. Great. You've figured out the zero position in the pole, and you've also figured out Kc was equal to 10 in the previous step. And thereby you have everything to put together the phase lead portion of your lead lag compensator, and that would be quantified as 10 times S plus 2.38 over S plus 8.34. Okay, that's fine. But there's another quantity that could be extracted from the pole and zero location, and that would be beta. Beta quantifies typically the scaling factor to relate the zero and the pole location of the lag compensator, yet here that same factor is used to relate the pole and the zero location of the lead portion. So if you were to take the ratio of those two things, so the pole versus the zero, that would end up giving you beta as a respective position, a positioning factor of 3.5042. A very important factor to do the last step of the entire design, step 5, which I would say just select T2 to complete the entire design of the lead lag compensator. So again, I like to use T2. You know, this is pretty much rule of thumb and experience, but T2 equal to 10 gives us good results most of the time, combined with beta equal to 3.504 as established by the respective position of the pole with respect to the zero for the lead portion. That would give us a lag, which is again S plus 1 over T2 over S plus 1 over beta T2. This is the lag on its own, meaning that with those two things you get a lag equal to S plus 0.1, so the 0 at minus 0.1 in complex plane, and with a pole 1 over 35.042 for the pole of the lag compensator, such that all in all the final compensator that would ensure that the transient performance is met and that the steady state tracking error is satisfied as well would be given by GC of S equal to 10 over S plus 2.38 with S plus 8.34 lead portion multiplied directly with the lag S plus 0.1, S plus, if you evaluate this fraction, that would give you something. Okay, that's it. Lead, lag, compensator as a single unit, designed with a new methodology that arises from selecting gamma exactly equal to beta. And in my opinion, this is a very interesting design methodology. But always keep in mind that there is the first design case, which is perhaps a bit more intuitive for you because that's only combining the previous design methodology for the lead as a standalone with the lag compensator as a standalone unit as well, and merging both together with very subtle nuances introduced in the methodology. Yet both design cases will give you a good design in terms of satisfying the transient and the steady state performance. That's it for today. Hope it makes sense to you. Hope you enjoyed this one. And until then, keep up the good work. I'll see you soon.